By the way, one of the things that I'm actually going to give you a kind of a small science lesson by talking about USA Today. Now, I bought this last Friday afternoon. And because I like doing the crossword puzzles and reading about the NFL games, the previews, but I was so busy that I didn't get a chance to read it. And I was in my easy chair at home, and I looked over, there it was, it hadn't even been open. So what I'm going to do is read it now and compare the predictions of the NFL games and college games, actually, that they made in here and compare it to what actually happened. The reason I bring that up is because I have emphasized to you that the entire scientific enterprise, as established by Professor Galileo, is concerned in large part with predicting the future dynamical state of some physical system. And we're going to be talking about that today. And it is way easier than predicting a football game. A football game is extremely complicated. So you might, everybody thinks, well, scientists, they're really smart and stuff. But we're the guys that actually, we've just scoped out the easy stuff. So compared to this football games. You guys in the ties back there, white shirts and ties, you ready for class? You ready? Are you guys in a sorority or fraternity, I mean? Okay, fraternity boys, pay attention. I'm lecturing. You should be paying attention to what I'm saying. All right. The office hours situation. Darien has office hours at 1 o'clock to 2 o'clock p.m. on Mondays in the atrium of the Physical Sciences Building. This is the Physical Sciences Building, in case you haven't been over there. It's like, okay, you go, Sumter Hall and the Counseling Center, if you know where those are, and then you just keep going towards the bus stop, the shuttle bus stop, that's right by the Physical Sciences Building. And I'm over there, it says 10:30 a.m. to noon. That's wrong. It should be 11 a.m. to 1 p.m. for me. Anyways, Darien will be in the atrium at 1 p.m. on Mondays for your studying activity with her, and I highly recommend it. She's very smart. She's of course, very friendly. Okay, last time. We talked about the law of universal gravitation in the context of A, a force with F equals ma, and B, in the context of centripetal acceleration and centripetal force. And we talked about how Sir Isaac Newton developed it. And I made up a picture here. I want you to look at this diagram really carefully. This particular diagram here has a picture of the Earth, this little dot in the upper left. And then way down here is the moon, a little circle to represent the moon. And then, of course, this dotted line represents the distance r between them. Sir Isaac Newton figured out that gravity that pulls an apple towards the Earth is also the force that keeps the moon on its circular orbit. And the reason I'm showing you this diagram here today is, here's the moon down here and the Earth up here, is because this particular diagram shows the Earth and the moon diameters, in other words, their sizes in proportion, and also the distance. So if you could get into a spacecraft and head towards the North Star for a few million miles and looked back at Earth and the moon, it would look about like this. Okay? And of course, you'd see it in a dark background and everything. But that's the true proportions. It's amazing when you think about it, how small the moon is compared to the Earth. And what's really big is the distance between Earth and the moon. So this is a good diagram of their sizes and their distances. Another thing that we talked about last time was the concept of momentum, around page 45, and the impulse equation. Now, I want to emphasize a few finer points that we talked about in office hours yesterday, and that is with the impulse equation, this being the impulse on the left, F delta t, and the change in momentum, of course, being delta p. There's some variations of that we should just emphasize or connect to that standard form of it. First variation is instead of writing delta p, write in delta mv in parentheses. That's what the momentum is. And this is actually the form that those guys at Houston, figuring out the path of a rocket and the satellite and everything, they have to account for the change in the mass as well. So they work with this form. For us, we're going to consider our systems to be constant mass. So the only change is really the change in the velocity, delta v. And of course, that delta v is the same thing as v2 minus v1. It's always later minus earlier. So another way that you could write it is delta v, vf minus vi, v final minus v initial. And the other concept that I want to emphasize with you last time, and I'll reemphasize now, is that the impulse equation is a lot of times the easiest way to figure out a stopping time problem. So if you know that something's in motion and then it's stopped by friction or by somebody pulling on a rope or some other force, you can figure out the stopping time by using this equation. Another thing that you can do is actually figure out, well, how big is my stopping force given a certain amount of momentum and a certain stopping time? So you can kind of experiment, how slowly do I have to stop it before I get too much stopping force? Because that's the analogy with the snowdrift and the brick wall. If you stop a car quickly in a brick wall, the stopping force is so big, it'll damage the front end of your vehicle. But if you stop in a snowdrift and come to a nice, easy stop over the time to rest, maybe a second or two to stop, maybe even longer than that, the stopping force is going to be so small, it probably doesn't even dent your car even a tiny bit. Okay, so now in this idea that the easiest way to compute stopping time, delta t, I want you to look at this version, and I just chose one of them from the stack from the previous slide. If you can figure out 4 of the 5 items in this equation, then you can figure out the unknown 5th item. So for instance, if you know the force, the mass of your object, whether it's a baseball or a spaceship or a football or anything, and you know the 2 velocities, v2 and v1, then yeah, you can blaze this guy up. You can get delta t, stopping time, no problem. All right. And if you know the stopping time, but you need to figure out the final velocity or something like that, yeah, you can do that too. If you know 4 of these 5, you can get the 5th one. Just a little bit of algebra and a little bit of calculator time, and we were doing that yesterday in office hours. By the way, we had a good bunch of students, pretty much the whole time in office hours. And something I want to emphasize also to you: if you can come to 30 minutes of office hour and then you have to bolt and head out to your next class, that's fine. Just come and study for 30 minutes. Same thing with Darian. If you can only make it from 1:30 to 2, I'm sure she'll help you out for those 30 minutes. And I think that's also the same thing for SI. Go to as many SIs you can make. If you can just make 1 per week, or if you can only make the last 30 minutes of the Mondays and the Wednesdays, That's good. Now, hopefully, almost everybody will be able to look at the recordings of the online session, but the online session is a regular SI, and you can, I think that's on Wednesdays, Wednesday afternoons, just before dinner time. And hopefully you'll be able to benefit from that, even if you just look at the recording of it. Now, get your clickers out. I want to try some impulse calculations. See if your brain is on the run. All right. So remember, clicking in class, and if you've seen your clicking pointage on the test, you're good. You're registered. I know I know the serial number that you've got, and I know that it connects to you. If you got like a -1 on your clicking on the exam, you need to see me about registering your device. Same thing with the participation pointage. Okay, here we go. Question number 1 for today. You observe a large 4.5 kilogram blob of Jell-O. Read it carefully. All right, I see students clicking in the answers. Good. Morgan, where are you? Morgan from office hours yesterday. Are you here? I think she's in the second class. I see everybody else from office hours. That's good. 20 seconds. Should be actually very easy if you read carefully. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Let's see what you guys voted for. Whoa. Look at what we got here. We got a big spread. Now, if you look at that, that means that there's a little bit of tribulation here in terms of, what actually is the impulse. And for this one, it's simply the force, the tractor beam force, 12 newtons times 2 seconds. Okay, F delta T. There it is. All right, so a lot of you didn't get that one. Make sure you make a note of that. When you see impulse, think of a force times an interaction time of some kind. Okay? And this is a fairly easy one. I mean, the moon and the earth are exchanging impulse constantly. F delta T, every second there's some impulse, but it's changing because of the orbits and stuff. They're not perfectly circular. All right, let's do another one. Now this one is a stopping time question. Let me start it for you. Give you a little more time on this one. Basketball has a mass of 0.800 kilograms. Actually, I think we'll work with 0.80, but I think a real basketball is a little bit lighter than that. Anyways, 0.800 kilograms, speed 22 meters per second. How many seconds to stop it? With a force of 11 newtons. And definitely consult with your neighbor if you need to, or to double check your answer or double check their answer. And that's very good to do. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You guys that came in late, are you clicking? Good. You just missed one. You should be good. All right, let's see what you guys voted for. Oh, brother. I guess you guys are geniuses. 1.6 seconds. Very good. But let me just, challenge you something. Here's the solution for it. If you missed the first one and you got the second one, you got some stuff to straighten out in your so-called minds. Anyways, using the impulse formula with the given information for this last problem, delta P is 17.6 minus 0, or actually 0 minus 17.6. So the 17.6 goes in here in the impulse equation, right here, 17.6, and then 11 newtons. All right? And so now I can solve for delta T if I just divide both sides by 11 newtons. And so that works out to 1.6 seconds, and most of you got that. All right, so that's a good little mini review from the homework and stuff. And let me just make another little short announcement. There was a little bit of problem with, I think number 3, the baseball problem on the homework. And what happened was the Canvas software where I transfer a formula-based question like that from one test bank to the test bank for this class, it sometimes translates it as a fill-in-the-blank answer. In other words, it's in the first test bank, it's a formula, and it works perfectly. And then when I import it to the new test bank, for some reason it swaps it over to, I don't know how to prevent it. Anyway, so for some of you that were spinning your wheels on it last night, or I should say Tuesday afternoon, that's why it was blooping up. But I gave everybody another 2 opportunities to get that, and I think most of you are doing okay on it. All right, next topic is collisions and conservation of momentum. This is based on the impulse theory, but for a collision, what we're going to do is think of a collision of a closed system in which there's no net external forces. In other words, like the collision of boxcars in a freight yard. And so this is about page 47 in the e-textbook. And the idea is if the net force is 0, then the change in the momentum of the entire system is also going to be 0. And so there may be interaction forces inside the system. So it's possible to get some delta V's relative to other members of the system. And we're going to work at a system of boxcars. But in reality, you can do very, very similar calculations regarding molecules in a gas in which there's no net force. But there are plenty of interaction forces when the molecules bounce off of each other. So the idea of collisions and conservation of momentum come out of this impulse concept. Now, here's the example that we're going to work out. 4 boxcars, one of them moving at the start, number 1, and it's moving to the right, so it's got a vector v1 to represent its velocity, And in this example, I'm going to give it some velocity, 4.4 meters per second. Now, it's going to bang into a set of 3 boxcars that are at rest. So these babies have as a group, they're hooked up together, as boxcars usually are. And so they're at rest. If one of them's at rest and they're all hooked together, that means all of them are at rest. Similarly, after the interaction, after boxcar number 1 bangs into boxcar number 2 and hooks in to the string of boxcars, they're going to travel off at a different speed. Let's make a sketch of that. So the new group of 4, number 1 couples to the string of 3. They're linked together, but how fast is this new group of 4 going to move? So you might ask yourself, well, are they going to move at the same speed? Are they going to move at a slower speed? Are they going to move at a bigger speed? What is that new v subscript new velocity going to be after the interaction? Now, there's interaction forces, but nothing's unbalanced here. So there's gravity and the rigidity of the railroad track are, balance the vertical forces. And any force that number 1 pushes on the string of 3 with, the string of 3 pushes back with that same amount of force. So the third law pair is the string of 3 pushing to the left. Make a note of that. The string of 3 pushes boxcar 1 back to the left. Boxcar number 1 pushes the string of 3 to the right. Right? So we're now a little bit more complex relative to the skateboarder interaction, but it's very similar to the skateboarder interaction. So these interaction forces are present, no external net forces, but definitely these other ones. Now, I'm going to put in a hypothetical 35 metric tons, 35,000 kilograms for each boxcar. And 4.4 meters per second, I don't know, that's about 10 miles per hour. So that's a little fast, I guess, for a freight yard. I don't think they move them around quite that fast. But it's not too bad. Right? It is realistic. Okay, so we're going to figure out the final state, v subscript nu, based on our understanding of the interaction forces and the momentum states. So let's look at the momentum state before the interaction. Okay, P subscript I. Okay, each boxcar has 35,000 kilograms of mass, but only one of them's moving at 4.4. So that's this first term in the equation, 35,000 kilograms times 4.4. That's boxcar number 1. That's the one that's moving in. Now the other 3, they all have mass, but they don't have any velocity, so those are big goose eggs. So you have 3 goose eggs. Now normally you don't have to write those in, but I wrote them in to signify that each of those 3 boxcars has 0 momentum. All right? And that's the initial state. So you multiply that out. And do you have your calculators out? Better get them out today. You're going to need them. And just verify me on this 35,000 times 4.4. Anybody verify me on that? 154,000? Good. All right. And just start bringing your calculators to class. Now, if there's no external forces, the final momentum will be equal to the initial momentum. So 154,000 kilogram meters per second also has to equal the final momentum. Now the final momentum is a little bit different, so let's take a look at that. Because the final momentum, all 4 of those guys move off at a certain speed together. So the final momentum is 154,000 kilogram meters per second. And if you go by the definition of momentum, mv, the mass of the the group of 4 is 140,000 kilograms, 35,000 times 4. Okay, so it's like a big 140,000 kilogram, 140 metric ton object. But we don't know what V nu is. Not yet. But do you see how we can figure out? Raise your hand if you don't answer, but raise your hand if you can see how to get V nu. Do you see how to? Raise your hand if you can see how to get V nu. Good. Look at it carefully. Come on. Raise your hand if you can see how to get it. Think. How to get V? Okay, good. All right. Anybody else see how to get it? Okay, I see your hand over there. I see a bunch of hands. Remember, this is what you want to do. When you're in my class, you want to think. And hopefully, use the definition of momentum here. That's what this last move is. And let me just move this up now. And hopefully you decided, yeah, let's divide by 140,000 on both sides. So you have 154,000 kilogram meters per second divided by 140,000 kilograms. And hey, you guys, in this last expression, kilograms cancel. I don't have it installed on the slide, but you can mentally cancel kilogram from the numerator here, 154,000 kilogram meters per second, and cancel kilograms from the denominator, 140,000 kilograms. Okay, and that means you're left with meters per second of speed. And what does that work out to? Well, hopefully, anybody verify me on that? 1.1? Yeah, okay. Good, because you're going to have to do some calculations here in just a few minutes. I'm going to give you another example. So the conservation of momentum is the principle that we're talking about here. The skateboarders give another great example, and you can look at the skateboarder example at the beginning of chapter 4 and kind of think about it and check the momentum states, and you'll see that they also conserve linear momentum. The formal principle is the total momentum of a group of interacting objects remains the same in the absence of external forces. Now, if you have external forces, you're not going to have conserved momentum. But you can still work out F equals ma. There's no problem with that. All right? But in a lot of physical systems, like a galaxy, the momentum of a galaxy or an atom, the momentum state of an atom or an electron going around a nucleus, a lot of times you can think of those as systems in which momentum is conserved. All right. Now, let's try another set of boxcars on the iClicker. And let's see how you guys can tackle this. All right. So it's a set of 1 plus 3 again. Here's your question. Let me see if I can start this one. Hold on. Okay. And take a minute to work this one out. I'll turn the lights up for you. And consult. Can you guys read that? All right, let me turn the lights. Okay, so we'll have to. I guess you can work with each other. So I'll give you a couple minutes on this one. Yeah. What's that? Yeah, same thing. See the final state down there? Okay, same basic process. So same 3 boxcars a week later, and this time the ingoing speed of boxcar 1 is 6.4, so you can think of it that way. So whatever we did with 4.4, do that with 6.4. And you should be good. Get your calculator out. I'm glad to see you guys interacting with your neighbors and stuff. It's good. Something I love to see. See, because I know that, I yelled at the fraternity boys in the back row over there because they were blabbing. But see, now, if they're talking to each other and stuff, that is good. Because you guys learn extremely efficiently when you can interact. You ed majors, remember, whether you're secondary or elementary or early childhood, it's interaction with humans, or in my case, humanoid beings, that helps you learn. That's how you mediate learning. How are they doing over there? You guys got it? Well, let's see. You have a clicker, you have a calculator, and a cell phone. Excellent. I saw there's a calculus class down the hall, and I was sitting down the hall a little bit. I was going to get a Monster from the soda machine, but I forgot. But anyways, those guys, they were sitting next to me out in the hall, and boy, were they nervous because they have a test today, their first midterm in calculus class. Oh my goodness. Ooh, they were nervous. So they were all, making nervous jokes and, oh, I hate this stuff. Oh man, you know how it is.
So calculus doesn't test in the mall?
I guess not. They have written exams. They probably do that. They test in them all, but they probably also have written exams. So, what's that?
Pre-calc is definitely.
Is it?
Taught
Yeah.
this girl last time.
Yeah, pre-calc. Yeah, I could see that. Calculus is a tough class. I remember when I was an undergraduate. Oh my goodness. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Get your answers in. No slacking. All right, let me take a look here. All right. Question 3. Let's see if we can look down here. Looks like 76% of you got the correct answer, 1.6. Very good. All right, the rest of you jot down the answer, and I should have admonished you. Also, remember to write down, when we're doing a calculation problem like this, write it into your notes so you have it. And then if you get it wrong, you can write the right answer down and go back and check. Work it out again. Okay. This interaction of boxcars is a couple steps tougher than the interaction of the skateboarders. But as I mentioned to you, the skateboarder interaction example is typical. That's how scientists figure out complex interactions. Start with the simplest thing and then just gotta make your model more and more complicated and try to use F equals ma, conservation of momentum along the way, and see what you can see. Now, another tool that we use in studying the dynamical state of physical systems is energy. Question. I saw you holding up your notebook back there. Were you showing your classmates how to do something? That's good. That's good. I'm glad. You have a question? 140,000 kilograms is the mass, the total mass of the string of 4 boxcars. So they move off together as a set of 4. They look like 4, but you can think of it as one big object of 140,000 kilograms. And all the momentum is locked up in those 4 cars together. All right, next concept, next tool is energy. And if you want to make a note to yourself, textbook page 49 or so is where you want to look at that. And, I forgot to animate this. So let's just go through it step by step. We're talking about momentum and energy in a four-dimensional context, the context of space-time. And so item one, I just want to talk about a baseball on a free fall trajectory, which I've got pictured there. For every second of free fall, you get equal increments of downward speed because delta V is always negative 9.8 meters per second. That's what gravity tells you. Little g, negative 9.8 meters per second, negative 9.8 meters per second squared. So that means for every second of free fall, another negative 9.8 meters per second is added to your velocity. And that's whether you're going up or going down. In this case, we're thinking of just something dropping. But even in rising motion, you're losing speed. You're losing 9.8 meters per second for every second of free fall. Also, if you think about it, the baseball acquires equal increments of downward momentum. And in other words, m times v is negative 1.42 kilogram meters per second for a regulation baseball, 145 grams, 0.145 kilograms. So that's the delta V. So if you do your accounting on the basis of time, in other words, like a strobe, if you ever see a strobe photograph, they set the strobe light to flash every, tenth of a second or every thousandth of a second or every second, depending on what they set it. And you get a series of pictures of the motion of an object. Now, if you do things every second, hopefully you'll realize that the distance is not equal increments. So you can put that in item 1A, item 3. Vertical distances are not equally incremented if you do your counting second by second. Now, item B, if you do every meter, if you look at the free fall path meter by meter, then you get equal increments of v squared, and that's what we were working on in the homework. So v squared is 96.04 meters squared per second squared, as we saw in the homework. And those equal increments of v squared those are actually, after you do a lot of calculus and stuff, as I mentioned in the textbook, it works out to be equal increments of a quantity 1/2 mv squared. And that is called the kinetic energy. Okay, and that's the equation that we have in the right side of this slide. The change in the kinetic energy, delta KE, is also known as the work. Okay, so when a force does work on a baseball, gravity does work on a baseball, you do work on a shopping cart, pushing it through the grocery store. Your car does work on the transmission, and then that transfers to your wheels. Your car goes down the road. Well, that's known as work. And it changes basically it changes the speed. Now, I want to give you a little bit of background on what I mean by the four-dimensional nature of space-time, right? And we'll just take a look at this diagram here. Up here in the front of the room, this lectern, which I've tried to, draw a picture of, you can think of the horizontal side to left to right for you as the x-axis, and vertical floor to ceiling as the y-axis. And then you can think of the z-axis as going out in the direction of the aisle, either up this aisle or up that aisle, whichever one you want. Okay, so those are the three spatial dimensions. Okay, momentum has, or it's possible for momentum to have a little bit of momentum along each of those dimensions. So it's possible to have some kilogram meters per second of x-word along the x-axis momentum. And it's possible to have a little bit of kilogram meters per second, MV, along the y-axis. And it's possible to have some heading up the aisle, some z momentum. Okay, so those are the three spatial components of the momentum vector. They're all implied in that top formula. P with the arrow over the top of it implies a vector, and M with a V, and then V with an arrow over the top of it implies a vector, velocity vector. And the velocity vectors have three components, and so the momentum can have three components. Now that is extremely important when you think about the universe itself, which is has a four-dimensional structure. So what's momentum is a dynamical quantity. It's related to the motion and forces that an object experiences. In other words, a force changes a momentum given some time, some interaction time. So let's go over this four-dimensional space-time structure. Geometrically speaking, in four dimensions, you think of the three spatial dimensions, x, y, and z, like I mentioned with the lectern and the aisles and everything. And then the fourth dimension is time, t, the temporal dimension. All right? Now, I think many of you probably have heard of that. Time is the fourth dimension, they say. Now, corresponding to that, those are geometric quantities. The dynamical quantities, it turns out, are momentum and energy. Momentum is a mass times a spatial velocity. And in terms of an equation, P equals mv, as we've already mentioned. And then energy is the fourth part of the dynamical quantities that you would use to completely study four-dimensional space-time in which we find ourselves. And Einstein's the one that figured all this stuff. Well, he started it, and he figured out quite a bit of it. And then, of course, we're still working on it, really. We're still developing it. In other words, the stuff that I wrote my PhD thesis about involved the theory of space-time. So I'm kind of following, doing a little bit of sweeping up the floors after Einstein. He tackled most of it. He was a pretty smart guy. Anyway, so when we talk about energy, yeah, that famous equation, E equals mc squared, you've all seen it. Yeah, that's an energy equation. Kinetic energy, 1/2 mv squared. And there's a whole bunch of other forms. We'll speak of some of the forms of energy. Now, the word work denotes a special, it's not a kind of energy, but it denotes that energy states have changed. So work is measured in energy units, and so is kinetic energy and a few other different kinds of energies. Now, I want you to draw a generic path G, and just choose a dot on it over here, somewhere on one of the curves. And as we've done before, draw a velocity vector tangent to the path. And if our new dynamical quantity, energy and kinetic energy, is really on the money, it should look a little bit, or it should come into an equation that is reminiscent of the impulse formula. Now, it's not going to be the impulse formula, but it's going to look analogous to that, hopefully. All right, so the change in the kinetic energy, so we might think a force times a delta S. In other words, a delta S stands for the length of a segment of a path. So on path G, you have a bunch of little delta S's. They're not necessarily delta X, but they could be. They're not necessarily delta Y, but they could be. They're not necessarily delta Z, but they could be. But no matter what they are, the spatial increment, delta S, maybe a little bit of X and a little bit of Y, or a little bit of Y and a little bit of Z, or a little bit of all three, it's going to have a length and it's going to have a direction. And so the problem with this first look, F net times delta S, there's a problem with that. And that is the net force might be perpendicular to the path. Right? So go ahead and draw on a force acting at that point, a net force, and make it kind of slanted in. It is not tangent. All right? Matter of fact, this would be the net force on a Maserati or any other car that's accelerating through the curves and speeding up as it goes. It's got some newtons perpendicular to the path and some newtons parallel to the path. All right, so let's take a look at that. So what we want to do is look at the portion of that net force that's parallel to the path. And that's going to be the part that's important to us. So I'm going to blow up that net force and bring it down here to the bottom. All right. So I'm just going to copy it down there. It's straight to the right in this diagram. Now the velocity is up to the right. So what I'm going to do now is trace in a component of F net that is parallel right there. That's the component of F net that is parallel to the velocity, and therefore parallel to the path. All right, now, the velocity vector, is tilted at 45 degrees there, and this F parallel is tilted at 45 degrees, right? Now, there's a little bit more to this vector. It's got a little bit of force perpendicular to the path, all right? That would be perpendicular to the velocity, all right? Now, if you don't believe me, just take a look at this. Okay, let's make a right triangle here. Right, there's the right triangle. Okay, and here's the split. I've split it up into parallel and perpendicular. Here's the right triangle. All right, so eyeball that. And now I'm going to park my F parallel up here. I'm going to copy it and move it back up here. All right, so that's my F parallel. Right? And this is the portion of F net that changes the speed because it's in the same direction as the velocity. It'll make the velocity arrow longer. This one will. If it was the exact opposite direction, it would slow down the velocity vector and make it shorter. Right? Now, I have a calculator, or excuse me, an iClicker question for you. Let's see if I can befuddle your, well, let me see if I can burn your brains. But before we do that, let me pause for questions. Has anybody got a question on this? Okay, let's keep going. Question. The parallel component of the net force, what does the perpendicular component? F perpendicular. We don't really need it for the work to calculate the change in the kinetic energy. But we may as well remind ourselves what it does. 30 seconds. Think. Think, my students, think. Think, Natasha, think. You guys may think maybe ask yourself, well, Dr. B, why do you keep calling out students' names? And I'm not doing that for any particular reason except to practice the names that I see a face and I know the name. I'm going to try to use it so that I can remember it. I don't know everybody's name in here. I might not get to everybody's name, but I'll get to a lot of you. And I like doing that, to know your name. It's important. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Uh-oh, we got a little bit of a controversy here. We have some people voting for A and some voting for C. Okay, now if it's perpendicular to the velocity, it's not tilted towards the velocity or away from the velocity, so it can't do anything but change the direction. Remember, it's a F perpendicular. Another word for that is F subscript C, centripetal force. Centripetal force, perpendicular to the velocity, only changes the direction. So what that tells you is that F parallel changes the speed. There's two components. If your net force has a little bit of each, you'll get a little bit of directional change and a little bit of speed change. Now, the work is concerned with the speed, not necessarily the direction. Right? It's V squared. So if you're going 5 miles an hour to the north or 5 miles per hour to the west or any other direction, it doesn't matter, that you'll have the same kinetic energy. So let me get this. Let's keep going here. So here's the formula that we want to use. And down here, this is the generic delta S notation. Simply means a small segment, Sarah, of the path. Delta S. So it's kind of generic. It doesn't mean any particular coordinate system. What it means is, think of the path first, whether it's a straight X path, a straight Y path up and down, like free fall, or a Z path to and fro, to the front of the class or to the back of the class, or a mixture of the same. They'll all have a little, segment of the path to which the force may be parallel, and that is the component, F parallel, that changes the speed. And that shows up in the change in the kinetic energy state. If there's some newtons of F parallel, yep, the kinetic energy is going to change. It might go slower, it might go faster, but it's going to change. The kinetic energy is one of the items that on a vertical freefall path, from the top of the leaning tower of Pisa to the bottom, every meter of freefall, you get the same size increment of work, the same size increment of delta KE. Another thing that you get in equal increments is something called gravitational potential energy. And this has got a different formula than the work. The work of gravity is just mg delta y. Gravitational potential energy is minus mg delta y. And in this case, you have to use the minus sign with the value of G 9.8. The gravitational potential energy increases when delta y is positive, and that's increasing altitude. Mg delta y, that's a mass times an acceleration, so a newton, times a distance, a meter. So a newton meter is the metric unit of work, the metric unit of energy, metric unit of potential energy. Kinetic energy too. It decreases when y is negative. In other words, when you're losing altitude, you lose a little bit of Newton meters of potential energy. Now let me ask you a question. This is related to 1B. My statement to you is that gravitational potential energy decreases when something's falling. What kind of energy increases? Kinetic energy. Right? So make a side note to yourself. The kinetic energy will increase as you fall, but potential energy will decrease. It'll get smaller as you fall. And there's an important concept behind this. For every kilogram of mass of the object and every meter of altitude of the object, there's a specific energy state defined, and that's actually why we call it potential energy. We call it the energy of position. And there's a huge amount of calculus behind this concept that we're not going to go into, and actually we talked a little bit about it when we talked about that generic path and F parallel and the velocity and stuff like that. But the potential energy and the kinetic energy are like cousins. All right, they're both energies, but they're different. Kinetic energy, 1/2 mv squared, is the energy of motion. GPE, gravitational potential energy, is the gravitational energy of position. And be careful when you're working with gravity and GPE. Both of them use a negative number for G, negative 9.8 meters per second squared. And actually, you know what else? Capital W, that's a symbol for work. And be careful because we've also used capital W for the weight force. And capital W is also used for watts if we were talking about light bulbs and electrical circuits and stuff. So you got to be careful with capital W. The work is force times delta Y. So make a note to yourself over here in the first column, this formula up at the top, W equals mg delta Y, and G's got a negative 9.8 value in there. That's the F parallel times delta S. Delta S, in this case, it's a free fall trajectory, so we just call it delta Y. It's straight down. It's not a mixture or anything like that. And mg, that's the weight force. All right? It's downward. So when delta Y is downward, delta Y downward means delta Y decreasing. You have a negative number here for G, and if delta Y is negative, negative times negative is positive. So the work increases on the way down. And this is the formula that measures that. Now, if you're a baseball popped up straight from home plate, you're losing speed as you go up. Gravity's working against, gravity's doing negative work. So in that case, delta Y is positive. That's on the third line of the table here. Delta Y is positive because you're on the way up. And the product, mg delta Y, is negative. You're losing kinetic energy. So make a note. Down here, when I say that work decreases, another way of saying that is I'm losing kinetic energy on the way up, which you know that it does. It slows down. And by the same token here, the middle line of the table, second line, if you're on the way down and you get faster and faster, you get more and more kinetic energy. Brock? Y? Y coordinate. Up and down, yeah. Now let's go over here to GPE. The formula here has a minus sign in front of it, and that means it's the opposite. Go ahead and make a note of that. It's the opposite of the work done by gravity. Right? Again, we use negative 9.8. And we use delta y as the same as before. Delta y positive if you're on the way up. Delta y negative if you're on the way down. And GPE decreases with downward y. And you may say to yourself, Dr. B, how does that work? Well, look. You have a negative sign in front. And then G has a negative sign. And then if delta y is decreasing, or if y is decreasing, delta y is negative. So you have negative times negative times negative. That's a negative. Negative times negative is positive. Multiplied by another negative, you have a negative number. So GPE decreases on the way down. When you lift something up to a higher position and put it on the bookshelf, you're over at the library and you put a big book up on the top shelf, you're lifting it up to a higher position, and if you put it there, it's at rest and it's not moving. But as soon as you tip it to the side and so that it can fall, it'll rapidly acquire kinetic energy as it falls to the floor. So we say that up there, go ahead and make a note. It's not in the slides, but you can say this. Potential energy up on the bookshelf is high. Potential energy down on the floor when the book falls is 0. Right? You've lost it all. So you pick up a book, and you put it up on top of the bookshelf, you're actually storing energy in that book. That's why we call it potential energy. It's a form of energy, you're storing it, and now that thing, just by virtue of its position up on the bookshelf, it has energy. It's not kinetic energy, it's energy of position, and it will convert. So that's the thing that I want to emphasize to you. And on homework this afternoon, which I'll probably activate a little bit after the second lecture. I was hoping to get it activated by 10:30 today, or by 11:50, but couldn't quite get it ready. But you'll have the homework this afternoon. And you'll be working on energy and stuff like that, some easy and some tough ones. Just remember that kinetic energy is the energy of motion. And just before that book hits the floor, we're not done. Oh, we've got a bunch of stuff to talk about here. You kidding me? Forget about it. I see everybody putting their books away. No, not yet. It may be Thursday, but we're not. Anyways, so the kinetic energy is maximum just before that textbook hits the floor. But the potential energy is maximum when you put it up on the shelf. No kinetic, all potential. And then, hey, you guys, here's another note to put down. It's not in the slide, but you can put it down. Halfway from the bookshelf to the floor, you have 50% potential energy and 50% kinetic energy. Right? So if you have 20 Newton meters on the bookshelf of potential energy, go ahead and make a note of that. 20 Newton meters for your book on the bookshelf. Just before it hits the floor, it'll have 20 Newton meters of kinetic energy. And halfway between bookshelf and floor, it'll have 10 Newton meters of potential and 10 Newton meters of kinetic. And if you're a little higher than that, it'll have a little bit more potential than it has kinetic. And they just and that's the whole thing. My wonderful students, write this sentence down. It's pretty important. Potential energy and kinetic energy are conserved. Potential energy can be converted into kinetic energy and vice versa. A baseball on the way up converts kinetic energy into potential energy. And a baseball on the way down converts, it's up there at the apogee, all potential, no kinetic, and then it starts converting potential to kinetic on the way down. So a baseball converts potential energy to kinetic energy on the way down. And hey, you guys, let me just add one more point of enrichment, kind of a sneak preview. When we study the atom, we're going to be studying electrical potential energy. Have you ever heard the word volts? Yep, everybody's always heard. Like, oh man, that's 20,000 volts of electricity. Like for an electric fence or something, or like a scary monster movie. They're trying to destroy the monster. Rev it up to 20,000 volts or something like that. Okay, volts, that's related to electrical potential energy. It's not gravitational, it's electrical, but it's potential energy. Stopping distance? Yeah, you can use F equals ma if you want. 1/2 AT squared and F equals ma. You can work that, the skateboard problem, the skateboard example at the beginning of chapter 4, it doesn't have a stopping time, it just has a change in the momentum. But if we have a frictional force on those skateboarders to slow them down, we could have done kinetic energy states of those two guys. And you can work it out, F equals ma, but usually the work formula here, delta K E equals F parallel times delta X, usually that is the easiest one to use for the stopping distance. Right? So again, the strategy is figure out the change in the kinetic energy, from, like the velocity of the boxcars, and then figure out or look or read the problem carefully, and it'll say, okay, your frictional force is, like we had on the coin stopping problem, 0.020 newtons, and then you can figure out the stopping distance. And so putting all that stuff together, stopping distance, use the work formula. Stopping time, use the impulse formula. At least try using those first. Sometimes, if you want to do stopping distance using F equals ma, and you like doing it that way, and you want to keep things simple inside your mind, it's all right. But for my money, this is the easier one to use, simply because you have the distance right here. Distance related to the, and what's interesting? The concept that unites the dynamical quantity, or that connects the dynamical quantity to the geometric quantity, is a force. And that is something that even Sir Isaac Newton didn't really understand. Nobody really understand what forces are. But we know that they exist. We can measure them in the kinetic energy states, the momentum states, positions and times of an object or a dynamical system of objects. So we can dismiss early now. Homework 7 will be running early this afternoon. You're dismissed. I'll see you on Tuesday.